Good morning, students. Last class we discussed about the performance of a single phase transformer. That is nothing but the tests of single phase transformer, that is equal to OC test, SA test, open circuit test or no load test, short circuit test or impedance test. By using those two tests, we can determine the copper losses, iron losses, and also equivalent circuit, that is nothing but shunt branch parameters, series branch parameters, such that we have to draw the equivalent circuit of a single phase transformer, and also have to determine efficiency at any type of load, at any desired load, and also regulation for a given power factor. It may be a lagging or leading or unity power factor, right? So for that class, transformer topic is completed in our electrical technology third unit. So two sections will be there. First section, transformer. Second section, three-phase circuits, that is polyphase circuits, right? Today class we go for the polyphase circuits or three-phase circuits, right? So electrical technology topic is three-phase circuits. So in this three-phase circuit, the contents are balanced three-phase circuits. What is phase sequence? Star delta connections. Relation between the line and phase voltage, line and phase current. So these relation is according to star delta connections. So relation between the line voltage and phase voltage, and also line current and phase current. Now last one, measurement of active and reactive power, balanced, unbalanced. How can you measure the active power and reactive power? By using 2-watt-meter method. So these are the topics. So out of these topics, these two are the very important. Derive the relation between line voltage, phase voltage in star connection, otherwise delta connection. Derive the relation between line and phase currents in star connection or delta connection, whatever it may be, very important. And then they are asking measurement of how can you measure the active and reactive power by using 2-watt method. Explain. So these two are the most important questions. And coming to the 2 marks, what is phase sequence? What are the advantages of balanced three-phase circuits? What is phase? What is phase sequence? Difference between the star delta, right? Write the relation between line voltage and phase voltage like that in star connection, like that. They are asking 2 marks questions, right? And big questions, these two last two topics, that is relation between line and phase voltages in star or delta connection, relation between line and phase current in star or delta connections, right? Now we go for the first topic, that is introduction. Generally, three-phase system, that means it is one, a three-phase balanced system is one in which there are 2 or more equal voltages of the same frequency displayed equally in time phase. That means suppose 360 degrees, so by 3 is nothing but 120 degrees. So 2 or more voltages of the same frequency, 2 or more voltages of same frequency are displayed so equal in time phase, 120 degrees, 120 degrees, 120 degrees. That is nothing but a balanced three-phase system which supply power to loads connected to the line. In generally, for n-phase system, there are n equal voltages separated with an angle of 2 pi by n, 2 pi by n or 360 degrees by n. So suppose this 2 pi by n equation must be applicable to all type of three-phase system. Suppose if it is a two-phase system, there are two equal voltages. Suppose two-phase system, 2 pi, I mean 90 degrees, 90 degrees, 180 degrees. So for three-phase system, the angle is 2 pi by n or 360 degrees by n. Suppose 3 voltages, so 2 pi by 3, that is equal to 120 degrees, 120 degrees. Suppose system of 6 or more phases are used to polyphase rectifiers. Suppose more than 6 or 7 for polyphase rectifiers may be used, right? Why? Because more phases are used means to reduce the ripples. Generally, to reduce the harmonics, we are utilizing filters, but coming to the electrical system, so as phase sequence increases, so harmonics are reduces, or ripples may be reduced. But compared to all phases, that means 6 phase, 4 phase, but 3 phase is commonly used, most commonly used polyphase system for generation and transmission of power. So for our coming to the electrical system, for generation of electrical power, transmission of electrical power, so and utilization, distribution and utilization of electrical power, we may commonly use three-phase system, right? The three-phase system is a common use for generation, transmission, distribution and utilization of electrical energy. Generally, a system is said to be symmetrical or balanced, whatever it may be. A system is said to be symmetrical or balanced when the various voltages are equal to in magnitude and are displayed from one another by equal angles. Suppose three phases, angle is 2 pi by n, that is 2 pi by 3, that is equal to 120 degrees. Then we can say that it is a symmetrical or balanced system. So a system is said to be symmetrical or balanced such that the various voltages are equal in magnitude, and also that all voltages are displayed from one another with the same angle. Otherwise, they are unsymmetrical or unbalanced loads, unbalanced systems. So 2 marks important. What is symmetrical system or what is balanced system? Three-phase balanced system, define. So a system is said to be symmetrical or balanced such that all the voltages are in equal magnitude and all voltages are displayed one another with the same angle. So otherwise you can say that so given system is unsymmetrical and unbalanced system. Now in our syllabus a balanced system is given, unbalanced system is not there. That's why we discuss about the balanced system only. A balanced three-phase system consists of 3 equal voltages, right? V1, V2, V3 with a phase difference of as usual 2 pi by 3, that is equal to 120 degrees, which supply power to loads connect to the lines, right? A balanced three-phase system consists of 3 equal voltages with phase difference of 120 degrees, which supply power to loads connect to the lines. If the voltages are not equal and the phase difference is not equal to 120 degrees, then the system is said to be unbalanced or unsymmetrical, right? Generally, how can we express the three-phase system? Generally, we can express the three-phase system with a letters capital R, capital Y, capital B, R, capital A, capital B, capital C, ORR, capital X, capital Y, capital Z, ORR, numerical numbers 1, 2 or 3. Generally, to identify the three-phase system, so these letters are utilized: RYB, or ABC, or XYZ, or 1, 2, 3. Suppose in general, out of this, in general, we can utilize RYB. So each phases will be displayed with 120 degrees to one another. So ER, so with an angle of 120 degrees to EY. EY is an angle of 120 degrees to EB. EB is an angle of 120 degrees to ER. Right? So why? Because the angle of three-phase system for equal balanced system is 2 pi by n. For three-phase system 2 pi by 3, so that is equal to. So suppose look at the waveform. The three-phase waveform is shown in figure C, and this is a vector representation or phasor representation shown in the figure B. So coming to the waveform, so ER will be starting. I am taking ER as the reference. ER is the reference. From that 120 degrees is nothing but EY. From that 120 degrees is nothing but EB. From that 120 degrees is nothing but ER. So that's why I am taking ER as reference. So it will be starting from 0 and it will be so 180 degrees and 360 degrees. Right? Now ER is started at 0 degrees. What about EY? EY started at 120 degrees, right? So that's why this is the 2 pi by 3. So this dotted line will give the 2 pi by 3 is nothing but from 0 to 120 degrees is nothing but at that situation EY will be started. EY. So 2 pi by 3, 5 pi, 2 pi by 3, 5 pi by 3, and then this one. Again, from EY to 120 degrees, EB started. Otherwise, from ER 240 degrees, 120 plus 120, that is nothing but 240 degrees, EB will be started. So, right, from 0 to 240 degrees. So, this is 4 pi by 3 is the 240 degrees. At this situation, EB will be started. Now, we have to, so from this 4 pi by 3 to 5 pi minus 5 by 3, there is nothing but 120 degrees. So, and then go to the maximum value. Here, negative maximum, EY is there. Like this, we have to draw the three-phase balanced system. Each and every phase will started so 120 degrees to each other. Generally, ER, we are represented the, we have to represent the equation of every voltages ER or EY or EB may be represented with EM sin omega t. Now I am taking R as the reference, that's why there is no phase difference. So ER is equal to capital EM sin omega t, where capital EM is the maximum voltage, right? Sin omega t. Now that may be represented in a vectorical representation, that is equal to ER is equal to EM at an angle of 0 degrees. At an angle of 0 degrees. Similarly, EY is equal to EM sin omega t. What is the phase difference between ER and EY? 120 degrees. After ER, that's why minus 120 degrees. EY is equal to EM into sin omega t minus 120 degrees. That may be represented in a polar form or vector form. EY is equal to EM at an angle minus 120 degrees. And last one, EB. EB is equal to EM sin omega t minus 240 degrees. So, EB is equal to EM sin omega t minus 240. Why? Because B phasor will be 240 degrees after started from the ER. That is nothing but after 240 degrees, EB will be started. That's why EB is equal to EM sin omega t minus 240 degrees. That may be represented in vector form. EB is equal to EM sin minus 240. Otherwise, EM plus 120 counterclockwise direction. So EM minus 240. This is clockwise direction. Suppose you have to take in counterclockwise direction, EM plus 120. So like this, we have to represent the voltages, three-phase voltages, three voltages in the three-phase system. ER taken as the reference, that's why 0 degrees, phase is 0. EY, it will be started after 120 degrees, that's why minus 120. So EB will be started after 240 degrees from the ER. So that's why it will be taken as minus 240 degrees, right? So ER is equal to EM sin omega t, or ER is equal to EM at an angle 0 degrees. EY is equal to EM sin omega t minus 120 degrees, or EY is equal to EM at an angle minus 120 degrees. So EB is equal to EM sin omega t minus 240, otherwise EM sin omega t plus 120. That may be represented in EB is equal to EM sin at an angle minus 240, or EM at an angle plus 120 degrees. Like this, we have to represent the three voltages in the three-phase system, right? So now we can use RMS values to represent the balanced three-phase voltages by defining the RMS values. Generally, for AC systems, we are utilizing the RMS values, root mean square values. Suppose go for the DC systems, we are represent the voltages in average values. Average values. Coming to the AC system, we are represent the values in RMS values. We know that what is the RMS value, general RMS value is nothing but maximum value by root 2. RMS value is equal to maximum value by root 2. Then we have to represent the maximum value by 2. RMS value E is equal to EM by 2. Then ER is equal to E at an angle 0 degrees. So we may represent E into 1 plus J0. Cos 0, 1. Sin 0. Cos theta plus J sin theta. Cos 0, 1 plus J sin 0, 0. That's why I represent E into 1 plus J0. Then EY is equal to E at an angle minus 120 degrees. That is equal to E into, so cos 120 degrees minus 0.5. Sin 120 degrees. Sin 120 degrees, that is sin 90 plus 30, that is cos 30, minus cos 30, that is equal to root 3 by 2 minus 0.866. So ER is equal to 1 plus G into EM into 1 plus J0. EY is equal to EM into minus 0.5 minus J 0.866, right? Cos minus 120 plus J sin minus 120, right? So that may gives the minus 0.5 minus J 0.866. Similarly, EB, E at an angle minus 240, E at an angle plus 120 degrees, that is equal to E cos 120 plus J sin 120. So it may cos 120 minus 0.5 and J sin 120 J 0.866, right? For a three-phase balanced system, the three balanced voltages ER, EY, EB may be represented like this. The sum of the three voltages at any instant equal to 0. For a balanced system only, the sum of three voltages at any instant is equal to 0. That is equal to ER plus EY plus EB equal to 0. Right? Now, what is the phase sequence? Generally, it is the order in which phase voltages will attain the maximum values. Phase sequence is nothing but it is the order in which the phase voltages may attain their maximum values. So ER will represent maximum value at 90 degrees. Then so EY will represent maximum value at 4 pi by 3. EB represent 5 pi by 3, like that. So the definition of phase sequence is nothing but, so phase sequence is the order at which their voltages will attain their maximum values. From the figure, look at the figure, phasor diagram, waveform of a three-phase system. So it is seen that voltage A, that is phase A, or voltage R, that is phase A phase, R phase, will attain maximum value first and followed by the Y and then followed by the B. First phase R will get the maximum value, followed by the Y, followed by the B. Hence, the phase sequence is RYB. Hence, the phase sequence is RYB. We can say that phase sequence is RYB. Suppose, so we have to take first getting maximum value is Y is nothing but YBR. First maximum value getting by the three phases is nothing but Y phase, then followed by B, followed by R is nothing but the phase sequence is YBR. Suppose first getting maximum value is B phase, followed by R, followed by Y is nothing but BRY, like that. So RYB is the phase sequence whenever maximum value getting by the phase R. This is also evident from the phasor diagram, that is vector diagram, in which phasors are with positive direction of anti-clockwise rotation passes a fixed point is the order RYB, and look at this one like this, from this and this on also. That by using waveform we can say that the phase sequence is RYB. By using vector diagram also we can say that RYB, right? Mainly the phase sequence will depending upon the direction of rotation of coils in the magnetic field. The phase sequence will be depending upon the direction on the rotation of coils in the magnetic field. That means if the coils rotate in opposite direction, then the phase voltage attains maximum values in the order of ACB. Suppose in anti-clockwise direction, so this is RBY. Suppose clockwise direction, RYB. The phase sequence gets reversed with the direction of rotation. Then the voltage for this sequence can be represented as, so suppose it may be normal clockwise direction, phase sequence is RYB. Suppose in anti-clockwise direction, RBY. So at that time, suppose to change the phase sequence of the three-phase system, we can change the direction. That's enough. We can change the direction of a phase sequence such that the phase sequence gets reversed. Then the voltages may be represented as ER. ER is equal to EM sin omega t. As usual, this is the reference. And ER is equal to EM at an angle 0 degrees. Right? Then EB is equal to EM sin omega t minus 120 degrees. Right? So if it is reversed. Suppose in normal direction, this is minus 240 or plus 120. But in reverse direction, this is the minus 120 and this is the minus 240. So EB is equal to EM sin omega t minus 120 degrees. That is equal to EB is equal to EM at an angle minus 120 degrees. Now go for the EY. EY is minus 240 degrees from the ER in anti-clockwise direction. So that is EY is equal to EM sin omega t minus 240 degrees. Otherwise EM sin omega t plus 120 degrees. Right? That may be represented in polar form. EY is equal to EM at an angle minus 240. That is equal to EM at an angle plus 120 degrees. Right? So simply say that the phase sequence is nothing but it is the order at which the phase voltages attain their maximum values. So phase sequence may be represented in clockwise direction. So by using waveform or by using vector diagram. By using waveform means, so which voltage will getting maximum value first, that is the reference, followed by the remaining two. So in our diagram, R phase will get the maximum value, followed by Y, followed by B. Therefore, phase sequence is RYB. Suppose in reverse direction, the phase sequence is RBY. Suppose the reverse direction, we are taking the reverse direction, RBY. What is the equations? What is the phase voltage equation? Suppose normal direction, already studied in the former slide, right? So now simply say that the phase sequence voltages, that is nothing but that may be expressed in RMS values. The phase sequence RMS voltages can be expressed as ER is equal to E at an angle 0 degrees and EB is equal to E at an angle minus 120 degrees. EY is equal to E at an angle minus 240 degrees, right? In anti-clockwise direction. Clockwise direction already discussed in the last slide. So first of all, what are the advantages of polyphase systems generally? The advantage of polyphase systems important for 2 marks or 5 marks also. Polyphase transmission line requires less conductor material than the single phase line for transmission of same amount of power at the same voltage. So polyphase transmission line requires conductor material, that is copper material or ACSR material, may be less compared to the single phase system. For a same amount of power, for transmitting the same amount of power and same voltage. So next one is, for a given frame size of a polyphase machine gives high output than the single phase machine. Go for the rotating machines. So compare the single phase machine or 3-phase machine. 3-phase machine will give more output, higher output than the single phase machine. Now go for the another advantage. Polyphase induction motor have uniform torque, that is 3-phase induction motor may have uniform torque, whereas most of the single phase has pulsating torque. So polyphase induction motor having uniform torque, whereas single phase induction motors may having pulsating torque. Another advantage, polyphase induction motors are the self-starting and also more efficient, right? Why? Because so induction motor, so whenever the relative speed between the rotor and stator must be 0, and again it will be attain their speed. That's why induction motor is also called as asynchronous machine. So induction motor is 3-phase induction motor is a self-starting. So and is most efficient one. Why? Because 80% of the motors utilized in the industrial is 3-phase induction motors. On the other hand, single phase induction motor are not self-starting, right, and are less efficient. So 3-phase induction motors are self-starting, whereas single phase induction motors are not self-starting. 3-phase induction motors are more efficient, but single phase induction motor are not a more efficient, maybe less efficient. Next one, polyphase motors have good power factor than single phase motors, and it has a poor power factor, right? Polyphase motors have a good power factor, but single phase induction motor does not having a good power factor. So for that we are using another extra equipment to improve the power factor of a single phase motors. Now we're coming to the most important topic, that is winding connections. For 3-phase system, there are 2 common type of interconnections are employed. First one, star connection or Y connection. Second one, star connection or Y connection. Look at the figure. So we are having 3 phases R, Y, B, right? R phase, one side of the R phase is connected to the line, another side of the R phase is connected to the neutral, one common point. Similarly, B phase is also, one phase is connected to the line, another phase is connected to the same common point. And Y is also connected to the, one side of Y is connected to the line, another one is connected to the same common point. That means all 3 phases R, Y, B, one side of all 3 phases are connected to the line, and the remaining side of all 3 phases will be connected at one single point. That is point is called neutral point. So we can call it as one side of R phase is R, another side of R phase is R dash. One side of Y phase is Y, another side of Y phase is Y dash. One side of B phase is B, another side of B phase is B dash. Now we connected RYB to the three phase supplies. Another side, that is R dash, Y dash, B dash are melting at one point, meeting at one point. That point is called neutral point. Neutral point. So this is three phase, three wire star connected system. Three phase, three wire star connected system. Now this star connected may be connected in another, that is three phase, four wire also. Three phase, three wire is nothing but three wires, R wire, Y wire and B wire. But now coming to the three phase, four wire, a extra terminal is needed, that is the neutral terminal, RYBN. So three phase, four wire star connected. So RYBN. Like this we have to represent the star polyphase star connected system. So polyphase, three phase, three wire star connected, as well as three phase, four wire star connected system. So another connection is delta connection. Delta connected, or it may be a so look at the figure clearly. Whereas in star connection, one side of all three phases are connected to the line, another side of all three phases may be meeting at one point, that point is called neutral point. But coming to the delta connection, so all three phases are bunched together to form a triangular shape or delta shape. So one side of R is connected to the another side of B, another side of R is connected to the one side of Y. That means R B dash meeting at one point, R dash Y meeting at one point, B Y dash meeting at one point. That means all three phases bunched together to form a delta connection. Now from that common points of every two phases, you have to take in the line. So R B dash taken one wire, that is taken as R phase, and Y R dash taken as Y phase, and B Y dash taken as B phase. That is nothing but RYB. It is always three phase, three wire supply. Then delta connection, there is no common point or there is no neutral point. That is the main difference. In star connection, neutral point is there. In delta connection, there is no neutral point. So that's why mainly delta connection is used in transmission system, and whereas in star connection may be used in distribution system, distribution of electrical power. This is transmission of electrical power. Now go for the important derivation, that is the phase line voltages and relation between the phase and line voltages and phase and line currents of a star connection. Very important. The phase voltage in star connection is also line to neutral voltages. Generally in star connection, the voltages are different. I mean, phase voltage is equal to line voltage by √3. Coming to the currents, both are same. Line current is equal to phase current, right? So generally the phase voltages, that is VRN, VYN, VBN, is all are same. That is, the phase voltage may be designated or represented in VP or V phase or VP. That is equal to VRN equal to modulus of ERN equal to modulus VYN equal to modulus BN is equal to VP. So where as usual generally we have to taken as the reference, that is equal to always R phase is taken as a reference. R phase is taken as a reference generally. Therefore, VRN is equal to VP at an angle 0 degrees, that is VP 1 plus J0. Similarly, VYN, VP at an angle minus 120 degrees. I am taking like this clockwise direction. VRN is equal to VP angle 0 degrees. So this is a voltage, phase voltage. Represented in, this is in polar form and it is represented in rectangular form, that is equal to Vp into cos 0 plus j sin 0, that is Vp into 1 plus j 0. Then Vyn is equal to Vp at an angle minus 120, that is equal to Vp cos minus 120 plus j sin minus 120, that may gives Vp into minus 0.5 minus j 0.866. Vbn is equal to Vp at an angle minus 240 degrees or Vp at an angle plus 120 degrees, that may getting the value Vp minus 0.5 plus j 0.866, right? Look at the figure phasor diagram. So I am taking first reference as Vr, right? So this is the first, generally you have to write the phase voltages Vrn, Vyn, Vbn. Generally you have to write the phase voltages first Vrn. So this phasor diagram is very easy, just please observe the diagram clearly. First taken as reference, that's why Vrn. From that Vrn 120 degrees, so from that Vrn 120 degrees is nothing but Vyn. From that Vyn, so it will be having another 120 degrees, that is Vbn. Otherwise, from Vr plus 120 taken as Vbn. Taken as first Vrn, Vyn, Vbn, such that the three phase voltages may be displayed with a 120 degrees. Right? And what are the line voltages? We have taken Vry, two phases. There is nothing but line voltage. One phase, one neutral is nothing but, so phase to neutral voltage, phase voltage. So Vry, Vyb, Vbr are the line voltages. Therefore, all are equal. That is Vry is equal to Vyb is equal to Vbr is equal to VL. Here the current, line current is equal to phase current. Line current is equal to phase current. So how can you generally, please, you can take it as capital. I am taking, this is Vrn, exactly opposite minus Vrn. Now Vbn and Vrn, the vector sum of Vbn and Vrn is nothing but Nn cancel to each other, Vbr is the line voltage. Similarly, this is Vrn and this is Vyn, exact opposite vector is minus Vyn. Now vector sum of these two voltages, that is Vrn and Vyn, is nothing but Vry. Similarly, Vyn is there. Now I have taken Vbn opposite vector, that is minus Vbn. Now vector sum of Vyn and minus Vbn is nothing but Vyb. Like that you have to determine the all line voltages. So generally from three-phase system, it is clearly observed that whatever current flows through the lines RYB also flows through the respective phase windings. That's why, hence, in star connected system, the phase currents and line currents are equal to each other. So I phase is equal to I line, that is the line current is equal to phase current. Now the voltage Vry between the lines R and Y is obtained by adding. So this is Vry. So this is the Vry. Vr and Vy, this is nothing but Vry. Vry is getting by adding the vectors Vrn and Vyn vectorically. So Vrn is equal to generally Vrn minus Vyn. So then similarly Vbr is equal to Vbn minus Vrn. Similarly, Vyb is equal to Vyn minus Vbn. Right? The line voltages Vry is obtained by adding Van and minus reverse vector of reversed vector of Vyn. So therefore, Vry bisects the angle of Van and Vbn. Look at the figure. These bisect. This is from Vrn to Vbn 120 degrees. This is exact middle. So angle between Vrn and minus Vyn is 60 degrees. Now this Vry is the middle in between these two. That's why 30 degrees. 30 degrees. Therefore, Vry is equal to root 3 V phase at an angle 30 degrees. That is root 3 V phase sin omega t plus 30 degrees. Will be called omega t plus 30 degrees. That is nothing but Vry square is equal to Vrn square plus V minus of Vyn square plus 2 Vrn Vyn cos 60 degrees. Cos 60 degrees. That is equal to line voltage is equal to root 3 Vry square is equal to 3 Vrn square. Therefore, line voltage is equal to Vry is equal to root 3 Vrn. So line voltage is equal to root 3 phase voltage. Otherwise, phase voltage is equal to line voltage by root 3. Remember, for star connection, voltage is different. Line voltage is equal to root 3 phase voltage, but currents are equal. Line current is equal to phase current. Similarly, Vyb is equal to root 3 V phase. So look at the figure, minus 90 degrees. So this is 30 degrees. That's why at an angle 30 degrees, but it is 90 degrees, minus 90 degrees. Otherwise, root 3 V phase sin omega t minus 90. Vbr, root 3 V phase sin minus 210. So that means root 3 Vp minus 210 or 150. So root 3 Vp sin omega t minus 210. Check all these three line voltages. For a three-phase balanced system, Vry plus Vyb plus Vbr equal to 0. Already discussed in the last slide. So after checking all these things, so we are getting a Vry plus Vyb plus Vbr equal to 0. Then given system is a balanced system. Like this, we have to derive the relation between the phase voltage and line voltage and phase voltage, line current and phase current in a star connected system. Similarly, delta connection, similarly same derivation, delta connection, V line is equal to V phase. In delta connection, voltage is same, line voltage is equal to phase voltage, and but in current is different. Line current is equal to root 3 phase current. So similar derivation as usual. As we discussed in the star connection, is here also same. Line current is equal to root 3 phase current. So line current is equal to root 3 phase current, right? Current flowing through the phase windings, I RR dash, I BB dash, I YY dash, right? So are called phase currents and are balanced as shown in the phasor diagram. Look at the phasor diagram. Similar phasor diagram as usual as star connection. Applying KCL at node A, that is equal to IA plus ICA. I mean IR plus IBR is equal to IRY into IR. So from that we are getting the relations. Similarly, applying KCL at node Y and nodes B also. At node R we are applying. So these IRY is incoming current, IR is outgoing, IBR also outgoing. Therefore, at node R applying KCL, incoming current is equal to sum of two leaving currents, that is equal to IR is equal to IRY is equal to IR plus IBR. Similarly, apply KCL at node Y and also node B such that we are getting IY is equal to Iy is equal to IRB, IYB, it is incoming, IYB is incoming, so and then this is leaving. Similarly, at B phase, at B we are applying KCL, IBR is incoming and IYR and IB will be outgoing. So from that equations, so IA square is IR square is equal to, that is I line square is equal to I phase square plus I phase square plus 2 I phase square cos 60 degrees. From that we are getting line current is equal to root 3 phase current. Now we have to develop individual phase voltages, phase currents. Iy is equal to root 3 Ip at an angle 30 degrees. That may be represented in root 3 Ip sin omega t plus 30 degrees. Ib is equal to root 3 Ip at an angle minus 90 degrees. That is equal to root 3 Ip sin omega t minus 90 degrees. Similarly, IR root 3 Ip minus 210 degrees. So this is represented in root 3 Ip sin omega t minus 210. Sum of these three balanced currents IR plus Iy plus Ib equal to 0, such that given delta system is also a balanced system. Why line voltage is equal to phase voltage is nothing but the voltage across any two terminals corresponding to one of the phase voltage. The voltage across any two terminals corresponding to any one of the phase voltages. That's why hence in delta connection line voltage phase voltage are equal to each other. So in star connection currents are equal, delta connection voltages are equal. In star connection voltages are different, that is VL is equal to root 3 V phase. In delta connection currents are different, that is IL is equal to root 3 I phase, right? Thank you one and all. So in this video, the last discussed star relation between the phase voltage and line voltages, phase current and line currents in star connection and delta connection individually very important. Derivation is so very important, damn sure question. So please go through clearly and write down the derivation. I am giving the notes, right? Next class we will go for the last topic, that is measurement of active and reactive power by using 2-watt meter method. So to see this video, please subscribe DBS Talks.